Let's consider problem 7.47 of Sonntag. It is given that an air conditioner provides 1 kg per second of air at 15 degrees Celsius, cooled from outside atmospheric air at 35 degrees Celsius. So clearly we have a room which is maintained at 15 degrees Celsius, and the heat exchanger is somehow able to extract the amount of heat and the rest of the cycle follows. Okay, so this is at 35 degrees Celsius, which is estimated to be the ambient, rather it is given as the ambient. Okay, so what is the amount of heat transfer required to cool air from 35 degrees Celsius to 15 degrees Celsius? The flow rate is this. So Q dot equal to m air Cp delta T, which is equal to 1 into the Cp of air can be estimated as follows. Rather it should be the average of 35 and 15. So the average of 35 and 15 is equal to 40, 50, 25 degrees Celsius. Yeah, that's right. So let's see, it's 1.005. okay, that's fair enough. That's a standard value, 1.005. it is kilojoule per kg Kelvin. This is 1 kg per second. So the delta T is equal to 20 Kelvin. So Kelvin, kg, kg. So this is approximately equal to 20 kilowatt. So the heat that must be extracted is equal to 20 kilowatt. So if we just focus on the cycle, there is some work input to the air conditioning system. It is extracting an amount of heat equal to 20 kilowatt. It is giving something to the ambient. Clearly, for the cycle itself, we can assume that this is heat is being extracted at 15 degrees Celsius, which is not the case. Okay, and heat is being exited at 35 degrees Celsius. So what is the maximum possible efficiency? So beta is equal to QL by W, which is equal to TL by TH minus TL. Okay, so the coefficient of performance beta is equal to TL divided by TH minus TL, where TH is equal to 35 plus 276.13, TL is equal to 15 plus 273.16. That will give us the maximum possible efficiency of 12. The coefficient of performance is equal to 12.55, which is equal to 20 kilowatt divided by the net work input. So the work input required is equal to, so the work input is equal to the QL, which is equal to 20 by beta. Okay, as simple as that. Okay, so this is the estimate of the power. So the power required is approximately 1.594 kilowatt. So the work estimate that we obtain is equal to 1.594 kilowatt. But here the assumptions were, assumption was that the cycle is a Carnot cycle, and the temperature of the lower temperature reservoir is 15 degrees Celsius and the higher temperature reservoir is 35 degrees Celsius. But these are the room, this is the room, and this is the ambient, which are at 35 degrees Celsius. But for the heat exchanger of the air conditioning system to operate at such conditions, so the heat exchanger has to extract heat from 15 degrees Celsius and the ambient has to receive heat at 35 degrees Celsius. Therefore, the temperature at which the refrigerant will actually operate has to be greater than 35 degrees Celsius, because the heat has to be transferred from the heat exchanger to the ambient. So this temperature must be, suppose, 50 degrees Celsius or something greater than 35. Similarly, this temperature has to be less than 15 degrees Celsius. So this temperature, suppose, has to be 5 degrees Celsius. Therefore, this is a very conservative estimate. This is a very conservative estimate. Rather, it's not a conservative estimate, it's a very lower bound on the estimate, because of these external irreversibilities. For the finite temperature differences, finite delta T is for the heat transfers, finite delta T is required. That will actually cause irreversibilities, and one would require in reality larger amount of work to be done. Okay, that is the crux of the problem. However, if we assume everything as ideal, that the work output is equal to the work input is equal to 1.594 kilowatt.